This video is going to go over section 2.2 notes. It asks us to use the graph to determine the following questions. So here's our graph. The first question is domain. Remember, domain is our x values. And we're going to write this in interval notation, so we have to look at our graph from left to right. So from least to greatest, so our smallest to our largest x values. So if you notice, our graph is going on forever on the left-hand side. So it's going towards towards negative infinity. So from negative infinity, we can never include negative infinity, so we're going to use a parenthesis there. Our graph's going to go over, it's going to go down. That's okay. I'm just worried about what's happening on the right-hand side. So if you notice, our graph is going up, and it's slowly going towards the right forever. So it's going from negative infinity. It's not stopping anywhere on our right-hand side, so it's going on forever to the right, so it's going towards positive infinity. So our domain is from negative to positive infinity. Question B says our range. Our range is our y values. Again, we have to write our y values from least to greatest. Our smallest y values are at the bottom. So we're going to start at the bottom, and then we're going to work our way to the top of the graph. So looking at a graph from the bottom to top. So the bottom of our graph, our smallest y value happens right here. This is the ordered pair 3, -1. So -1 is my smallest y value. There is a point there, so -1 is included. We're going to use a bracket. And then my graph is going over that way. That's fine. I don't really care. So it's going up forever this way. So because it's going up forever, it's going towards positive infinity. So from -1 towards positive infinity is our range. Again, for infinity, we can never reach infinity, so it cannot be included. So a parenthesis there. So as long as one side goes up forever, that's all I care about. So that's my positive infinity. My x-intercept, so where does my graph hit my x-axis? So this is the points that cross or touch x-axis. So right here is my 2 points that cross my x-axis. Those points are 2, 0 and 4, 0. So those are the points. As mentioned in 2.1 notes video, sometimes my math lab wants the ordered pairs, sometimes it just wants the x value. So in this case, x is 2 and x is 4. So 2, 4. Our y-intercept now, for example, D, this is the points that cross or touch our y-axis. So hitting our y-axis, we have this one point up here. So this point will give us 0, 8. So that point is 0, 8. And if it just wants the value, our y value is going to be 8. So just 8. Example E says f of 6. So it tells me my x value is 6. What is my y value? So when x is 6, we're looking at this. When x is 6, I was getting ahead of myself here. When x is 6, right here, we're looking at this x value. So here's when x is 6, going over. When x is 6, my y value will be 8. So this is the point 6, 8. So that value, f of 6, is going to equal 8. Example F, the value of x, so I need to try to find x, for which f of x equals 3. So here's telling me the y value is 3. When y is 3, what's my x value? So when y is 3, we're looking at this value right here. I see I have 2 points in which my y value is 3. This one is 1, 3, and this one's 5, 3. So for those, or y value is 3, x is 1, and x is 5. G, open intervals on which the function is increasing, if any. So it's asking us, where is the function increasing? When is it going upward? By the way, open intervals, we're still going to use interval notation like we did for domain and range, but it's saying like open circles. So open circles mean always use parentheses. So it's asking, where is this function going upward? So we're only going to look at x values. So I see that it's going upward, starting here, reading my graph from left to right, read from left to right, and then all the way it's going up forever. So this is where it's increasing. So there, my x value starts increasing right here at x equals 3. We said we're going to use parentheses, and then it's increasing on forever this way. So it's increasing on forever this way. And that x value is going on forever, so pos infinity. Of course, we can never include infinity, so that's always a parenthesis. But the reason why this 3 is a parenthesis, the reason why it's an open interval when it's always asking for these questions, at this point, it's changing. It's going downward, and then it's decreasing and it's increasing. So I only want it where it's increasing. So it starts increasing right here, but not at that exact point, because at that point is when it switches. So that's why we don't want to include 3. We want to use a parenthesis for that one. And it told us open intervals, so that tells us parentheses. Same thing for the open intervals on which the function is decreasing. So decreasing means it's going downward. So it's going downward, starting from here, all the way to there. So decreasing, going downward. So where is it going downward? Starting at our x value of 0. At 0, it's staying constant, and it starts to decrease. So we don't want to include that point because it's changing there. So I don't want to include that point. And then all the way, it stops going downward. It stops decreasing at our x value of 3. Again, at 3, it's going from decreasing to increasing. So that's when it's changing. So I don't want to include that point. So to show that it's not included, we're going to use a parenthesis. So it's decreasing from 0 to 3. Last but not least, on this type of example I says open intervals on which the function is staying constant. So constant means like it's flatlining out. So this is where my graph is staying constant. So where is it staying constant? What x values? It's going on forever to the left. So from negative infinity. And then it stops staying constant, starts going downward at x value of 0. So from negative infinity to 0 is when it's staying constant. Again, we're always looking at x values there. Example J, what is the number at which f has a relative maximum? So relative maximum. So maximum is a high point or a peak. So for example, if you had a graph that looked like this, up here, this high point would be our maximum. So looking at this graph, I see it staying constant, and then it starts going down, and it goes up forever. So there's not one point that's higher than another because it goes on forever. So there is no relative maximum. So there's no peaks in our graph. Here it's staying constant this whole time, so one is not higher than the other. And then it just goes on up forever towards infinity. So no high points, no peaks. Example K. What is the relative maximum of f? So it's saying, what is the number at which f has a relative maximum? Well, we said there wasn't a relative maximum, so none. So no maximum still. So just to differentiate these two, because it seems like they're asking the same problem. It says, what is the number at which, so where, f has a relative maximum? So this one's looking for x value. This is looking for x value. This is saying, what is the maximum? What is the highest point? What is the highest value? So this is asking for the y value. But there is no maximum point, so there's none for either one. With that being said, example L, what is the number at which f has a relative minimum? So minimum is a low point or a valley. So for example, if we had a graph that looked like this lowest point down here would be our minimum. This is saying, what is the number at which f has a relative minimum? So where is it at? So because it's looking for where it's at, it's asking for an x value. So minimum. So this point down here is our minimum, is our low point. We said that point was 3, -1. So this is going to have an x value of 3. And then what is the minimum? What is the lowest y value? And that's going to be our y value of -1. So for letter M, it's asking what is the lowest point, what is the relative minimum of f? So that's looking for our y value. The way the wording works, it's looking for x for L and then our y value for the question M. Last but not least, which interval or union of intervals, so which interval or intervals together represent the values for which f of x is less than or equal to 0. So when our y value is less than or equal to 0, because f of x is the same thing as y. So we are looking when our y values are below 0. So here's our 0. So when is y below 0? So it's below 0 from this point to this point. It's below 0 from this point to this point, which is from 2 to 4. So going from left to right, starting at 2, and it's going to 4. So because we have less than or equals to, that's automatically telling us to use brackets, but it's saying when is it less than or equal to 0? At 2 and 4 equals 0, so we want to include those points, so we're going to use a bracket there. Whew, we're finally done with that example. So the answer to the interval or union of intervals in which represent the values for which y is less than or equal to 0. The only points when it's less than or equal to 0 is this little piece right here. That little piece goes from 2 to 4 is our x values. It's asking where. Next example, it says determine whether the graph of the equation is symmetric with respect to the y-axis, the x-axis, the origin, more than one of these, or none of these. So example A says x squared plus y squared equals 15. We have a little note over here. I kind of gave you the little rules. So if it has y-axis symmetry, that means I can plug in -x, and then we're going to get xy out. We're going to get the original equation out. If it has x-axis symmetry, that means I can plug in -y, and we can get the original equation out. And lastly, if it has origin symmetry, I can plug in both x and -y, and I'll get the original out. So we have to test each one of these separately because there could be more than one. So for example A, we have x squared plus y squared equals 15. First testing to see if it has y-axis symmetry. So that means I'm going to plug in -x and see if I get the original equation back out. So plugging in -x, so -x squared plus y squared, y is going to stay the same, equals 15. So -x squared, so -x times -x is +x squared. So we're left with x squared plus y squared equals 15. That is the original. So the graph does have y-axis symmetry. So it does have y-axis symmetry. Now let's next test x-axis symmetry. For x-axis symmetry, I'm going to plug in negative y, and same thing, see if we get the original equation back out. So we have x squared plus negative y squared. We're plugging in negative y equals 15. We have x squared plus negative y squared. So negative y times negative y is positive y squared equals 15. This is the original, x squared plus y squared equals 15. So we have x-axis symmetry as well. And last but not least, we need to check to see if it has origin symmetry. For origin symmetry, we're going to plug in both negative x and negative y to see if we get the original out. Because we already plugged in negative x here and it worked, and we already plugged in negative y here and they both worked, this one usually works, but let's go ahead and test it out just to make sure, especially for our notes' sake. So plugging in negative x squared plus, again, plugging in negative y squared equals 15. Negative x squared is negative x times negative x, which is positive x squared, plus negative y squared is negative y times negative y, so that's positive y squared equals 15. That indeed gives us the original x squared plus y squared equals 15, so it also has origin symmetry. So this example had y-axis symmetry, x-axis symmetry, and origin symmetry. Example B, same thing. We're going to test y-axis, test x-axis, and then test the origin symmetry. So example B, it says x equals y squared plus 12. First testing y-axis symmetry. We're going to plug in negative x to see if we get the original equation out. So plug in negative x equals y squared plus 12. Unlike the previous problem, I can't do anything to get rid of this negative. It's just negative x equals y squared plus 12, so that's not the same as the original. So no y-axis symmetry. Testing x-axis symmetry. Oops. We are going to plug in negative y to see if we get the original equation out. So we have x equals negative y squared plus 12. So negative y squared, so negative y times negative y will give us positive y squared. So we have x equals y squared plus 12, which this is the original. So we do have x-axis symmetry. And then last but not least, testing to see if we have origin symmetry. So in the back of my mind, I'm thinking, okay, we plugged in negative x, it didn't work, so it's probably not going to work again. But let's just make sure, because there are some special cases where it does work. So plugging in negative x and negative y to see if we get the original out. Negative x equals negative y squared plus 12. I can't do anything to get rid of that negative x, so it's going to stay negative x. Negative y squared, so negative y times negative y is positive y squared plus 12. So we have negative x plus y, negative x equals y squared plus 12, which is not the original, so no origin symmetry. So example B only has x-axis symmetry. All right, next page. So determine whether the function's even, odd, or neither. So again, we have a little note on the side there, and it says if it's It's even if it has y-axis symmetry. Remember from the previous page that y-axis symmetry means that we can plug in negative x and we can get the original back out. And it's going to be odd if it has origin symmetry. So if I plug in negative x and negative y and get the original out. My biggest thing that I remember here is odd and origin, and then even and y-axis. So looking at this, we don't have an equation to plug in, but I can plug in 2 points. So like let's use this point. This point is going to be 3, 2. And this point over here, they correlate with each other, is negative 3, 2. And if you can see really small, they gave me those numbers. I'm just writing it a little bit bigger. So it's saying if my original is 3, 2, that's the same thing as negative 3, 2. So if I have x, y as my original, that's the same thing as now saying negative x, y, which is y-axis symmetry. So it's going to be even. Another way to think about this is if I take this graph and I fold it along the y-axis, so taking it and folding it this way along the y-axis, it's going to be the same thing on both sides. If I fold it this way, like hamburger style, that would be x-axis symmetry. And if I fold it both ways, it would be symmetric along our dotted, horizontal, x equals y. It would have origin symmetry. So kind of looking at the 2 points is our easy way of seeing, does it have y-axis symmetry or does it have origin symmetry or is it neither? So next example asks us to determine whether the function's even, odd, or neither. But now we're going to do algebraically, then determine whether the function's graph is symmetric with respect to the y-axis, the x-axis, or neither. So example A says f of x equals x to the 5th plus 5. So f of x is our y value, so y equals x to the 5th plus 5. To see if it's even, odd, or neither, we need to see what kind of symmetry it has. So let's go ahead and test first our y-axis symmetry. So for y-axis symmetry, we're going to plug in negative x to see if we get the original equation out. Just kind of like putting the 2 previous examples together into one. So plug in negative x, so y equals negative x to the 5th plus 5. Y equals negative x to the 5th, so negative x times negative x times negative x times negative x times negative x. That doesn't cancel out that negative, so it's still negative x to the 5th plus 5. Y equals negative x to the 5th plus 5 is not our original. So therefore it means not symmetric to y-axis with respect to the y-axis. So therefore also means it's not even. So it kind of kills 2 birds with 1 stone. Because even is y-axis symmetry, so we know if it doesn't have y-axis symmetry, it's not even. So next, testing x-axis symmetry. We're going to plug in negative y to see if we get the original equation out. So we have negative y equals x to the 5th plus 5. I can't do anything to get rid of that negative. So I have negative y equals x to the 5th plus 5. That's not the original. So no x-axis symmetry. X-axis doesn't tell me even, odd, or neither, so the only thing I know is that it's not symmetric with respect to the x-axis. So our last thing to check is origin symmetry to see if it's odd. So plugging in negative x and negative y to see if we get the original equation out. We have negative y equals negative x to the 5th plus 5. We have negative y, can't do anything to get rid of that negative, equals negative x to the 5th. Like we said up here, we can't get rid of that negative either. So negative x to the 5th plus 5. I have negative y equals negative x to the 5th plus 5. I can't do anything to get rid of the negatives. This is not the original. So no origin symmetry. Remember, origin symmetry means it's odd, so therefore also it's not odd. So it's going to be neither for everything. So it's not even, it's not odd, it's neither there. And doesn't have y-axis symmetry, doesn't have x-axis symmetry, it has no symmetry. So neither for both answers. Same thing for example B, we have g of x. G of x is the same thing as y, equals x squared minus 2. First testing y-axis symmetry. We're going to plug in negative x to see if we get the original equation out. So we have y equals negative x squared minus 2. So y equals negative x squared. So negative x times negative x is positive x squared minus 2. So we have y equals x squared minus 2, which is the original. So we have y-axis symmetry. So that means it's also even. So kind of know those two things in one. So we know it has y-axis symmetry and we know it's even. So next, testing x-axis symmetry. We're going to plug in negative y to see if we get the original out. So negative y equals x squared minus 2. I can't do anything to get rid of that negative in front of the y. So I'm left with negative y equals x squared minus 2, which is not the original. So no x-axis symmetry. And then last but not least, testing for origin symmetry. Remember, if it has origin symmetry, it is odd. For origin symmetry, we're going to plug in negative x and negative y. So negative y equals negative x squared minus 2. I can't do anything to get rid of that negative in front of the y, so it's going to stay negative y equals negative x squared. So negative x times negative x is positive x squared minus 2. So we're left with negative y equals x squared minus 2, which is not the original. So no origin symmetry, so that means it's not odd. So for example B, it had y-axis symmetry and was even. Okay, last one, example C. H of x equals x times the square root of 4 minus x to the 4th. Again, h of x is just the same thing as y, so y equals x times the square root of 4 minus x to the 4th. First testing y-axis symmetry. We're going to plug in negative x to see if we get the original equation out. So we have y equals negative x times the square root of 4 minus negative x to the 4th. So y equals, I can't do anything to get rid of this first negative in front of the x, so I'm just going to leave it negative x. The square root of 4 minus negative x to the 4th. So negative x times negative x cancel each other out. Negative x times negative x cancels out the negative. So this will give us positive x to the 4th power. So I'm left with y equals negative x square root of 4 minus x to the 4th. This is not the original. So that means it doesn't have y-axis symmetry, so it's not even. Next, testing x-axis symmetry. We are going to plug in negative y to see if we get the original equation back out. So negative y equals x times the square root of 4 minus x to the 4th. I can't do anything to get rid of that negative out front of y, so we're left with negative y equals x times the square root of 4 minus x to the fourth, which is not the original. So because it's not the original, it does, so no x-axis symmetry. Last but not least, testing origin symmetry. We're going to plug in negative x and negative y to see if we get the original out. So we have negative y equals negative x times the square root of 4 minus negative x to the fourth. Like we said earlier, we can't get rid of this negative out front of y, so it's going to stay negative y. Likewise, I can't get rid of this negative in front of x, so it's going to stay negative x times the square root of 4 minus negative x to the fourth, because that's the even power. Negative times negative times negative times negative will give me a positive x to the fourth. So I have negative y equals negative x times the square root of 4 minus x to the fourth. Now, I see that I have an extra negative on both sides. If I divide this side by negative 1, what do you do to one side, do to the other, divide that side by negative 1. That cancels out that negative. That other one cancels out the other negative. So we are left with y equals x times the square root of 4 minus x to the fourth, which is the original. So we have origin symmetry. So because there's origin symmetry, we know the equation is odd. So for example C, we have origin symmetry and it's odd. Last page, last two examples for this section. Evaluate the piecewise function at the given values of the independent variable. For independent variable, that's just our x. Then we're going to graph it, and then we're going to find the domain and range. So it's saying f of x. We have two pieces of the graph. If x is less than 0, we're going to plug it into 5x plus 3. If x is greater than or equal to 0, we're going to use 2x plus 7. So our first one, we have example A, f of negative 2. So our x value is negative 2. So negative 2 is less than 0. So because it's less than 0, we're going to use our first equation because that satisfies this condition. So we're going to use 5x plus 3. So plugging in negative 2, so 5 times negative 2 plus 3. So plugging this into our calculator, 5 times negative 2 plus 3 will give us negative 7. Boom. Next example B, it says f of 0. So this x value equals 0. We're going to use our second condition, our 2x plus 7, because x is greater than or equal to 0. So that means we're going to have to use 2x plus 7. We're going to plug in x is 0. So 2 times 0 plus 7 will give us positive 7. And lastly, we have f of 2. So our x value is positive 2. Positive 2 is greater than or equal to 0, so that means we're going to use this bottom equation of 2x plus 7. We're going to plug in positive 2. So 2 times 2 plus 7 will give us our answer of 11. So we evaluated the piecewise functions at the given independent variables. Now we're going to graph the function. So we have two pieces of our graph, so we're going to graph each piece separately. For this first piece, so just looking at this first piece, just looking at 5x plus 3 when x is less than 0. So let's use a little chart down here. So this 5x plus 3 piece for if x is less than 0. Little xy chart. We already plugged in 1 point, so let's use what we already have. So let's plug in negative 2, and we got out negative 7. Let's plug in another point so that way I can graph this. Let's plug in our endpoint. Our endpoint is 0. So 5 times 0 plus 3 will give us 3. So now I have two ordered pairs I can plot. So notice though, it's this 5x plus 3 is only if x is less than 0, not equals 2. So this 0 is not included, meaning we have to have an open circle. So I always want to do the endpoint to see where that open circle is at, to see where the end of my graph is at, but at that point it's going to be open circle because of the symbol. So -2, -7 is 1 point, and then 0, 3 is going to be our open circle. Connecting the dots. So it's going on forever in a negative direction. Oops. Boom. There's our graph. Maybe so you can see it a little bit better. So that's my endpoint. So you always have to plot your endpoint to see where the graph ends, and then it goes on forever. So any other point, we already plugged in -2, so we just went ahead and used that one. So that's our first piece. Second piece, 2x plus 7. And this is if x is greater than or equal to 0. So again, let's plug in a couple points. We already plugged in our endpoint. We already plugged in 0, and we got out 7. Notice that this 0 is included based off the symbol. It says greater than or equals to. So we're going to have a closed circle at this endpoint. Another point that we already plugged in was 2, and we got out 11. So 0, 7 is our first point, is our endpoint. We said it's going to be a closed circle. Our second point is 2, 11, so we'll just make do somewhere up there. Connecting the dots. That's our second piece of our graph. So together they make the whole function, but they're two separate pieces. The biggest thing is the endpoints. You have to plot these endpoints, whatever this number is right here. So you plugged in 0 for both of them because it was both 0. Based off this symbol, at 0 it's going to be an open circle. Based off this symbol, at 0 it's going to be a closed circle. Next is domain and range, which can be tricky for piecewise functions. So domain is x value, so we're looking from left to right. The left side of my graph is going down and like slowly over to the left forever. So it's going towards -infinity. The graph is coming up. At 0, it just stops here. It doesn't, but it jumps up here. So 0 is included, so 0 is okay. And it goes on forever to the right. So from negative to positive infinity. You can plug in any values for x. Our range is going down forever, so we have -infinity. And then it's stopping at 3. At 3, it's an open circle, so 3 is not included, so we're going to use a parenthesis. And then it starts up again, up here at +7. +7 is included, it's a closed circle, so we're going to use a bracket, and it's going up forever towards positive infinity. So it's saying y can be in this graph, or it can be in this graph. So we write the letter or as a capital U looking shape to unite those two intervals together. So we have -infinity to 3, or we have from 7 to infinity. For 3, we have a parenthesis, it's an open circle. For 7, we have a bracket because it's a closed circle. And infinities, of course, also always have parentheses. Last example for section 2.2. It asks us to find the difference quotient of f. The difference quotient is just this formula here. Which is f of x plus h minus f of x equals h, in which h cannot be 0 for the following function, f of x equals 2x plus 5. So for our difference quotient, we have f of x plus h minus f of x all over h. Looks big, bad, and scary. Let's just take it piece by piece. So this first piece is f of x plus h. We have f of x, but I don't have f of x plus h. So let's take our graph, just like we did earlier in section 2.1. Page 2 in our notes, going back, we plugged in x plus 2, and then we just solved it. Same thing here. We're going to plug in x plus h. So I have 2. Instead of x, I'm going to plug in x plus h plus 5. Simplifying this a little bit, let's distribute this 2. So I have 2 times x plus 2 times h plus 5. These are not like terms, so I cannot combine them. So f of x plus h is going to be 2x plus 2h plus 5 minus f of x. We know f of x is this 2x plus 5. That's all over h. Boom. So now we just have to simplify. Let's distribute this negative. So 2x plus 2h plus 5 minus 2x minus 5 all over h. Combining like terms, we have 2x minus 2x, so they're going to cancel each other out. We have 5 minus 5, again canceling each other out. We are left with 2h up top divided by h. Again, looky here, our h's cancel each other out. H divided by h is just 1, so we're left over with 2 as our final answer. So you'll see this a lot in pre-calculus and in calculus. We just found what's called the derivative of f of x, which is another word for the difference quotient. So kind of cool that you did something so complex just using algebra. So this is section 2.2 notes.